No.
What's the
Additive group. Well, it's additive group, yeah. A ring is an additive group that also has multiplication, satisfying certain, distributive properties.
I thought all
And for us,
so all
we
rings
also-
are not groups.
They are a group with respect to addition, not multiplication. There's usually not a inverse for every multiplicative. There's not a multiplicative inverse for everything in the ring, typically. But this what I'm trying to describe in ideal, it is a additive subgroup of the ring. All right, so like the sum of two things in the ideal has to be again in the ideal. All right, but it is it's not closed under just multiplication of the ideal. It's closed under multiplication from the whole ring. So what I was just telling you is it's much like a situation in group theory. An ideal is more analogous to a normal subgroup, right? Because normal subgroups, they're not just closed under multiplication of elements by themselves, but they're also, if you multiply anything in the group into a normal subgroup, it gives you back something in the normal subgroup, right? Same thing for the ideal, right? So like 3z is an ideal. In fact, so like if you take multiples of integers, it's an ideal.
Yeah, it's all like 3.
2z is also an ideal, right? 2z is an ideal.
Wouldn't any prime z be an ideal?
Oh, not it doesn't. Yeah, it doesn't even need to be prime. nz is an ideal.
Z. Yeah, I was thinking about inverses, and I was like, you can't inverse under.
Right. So in fact, nz is an ideal of z. In fact, you can prove that that's the only thing that can be an ideal of z. Like every ideal of z has the form n times multiples of n for some n. This is not too hard to prove.
For some n and z.
Hmm?
For some n and z.
Yeah, for some trace value. Now, so that's what an ideal is. I think it's important to tell you that because Nathan nowhere defined that, and you haven't had abstract algebra 2, so like it's a word that's just floating about, right? But that's what ideal means, okay? But the easiest way to create ideals is just to like take powers of an element. In a ring, if you have x as an element of the ring, then this usually denotes x to the n, Oh, excuse me, dummy. Yeah, x to the n. Sorry. Such that, Yeah, I'll say n equals to 0. That's what I'm thinking of. Sorry, I've had a sudden crisis of thinking. Let me stop that. Anyway, this would be the curses. It's bothering me because I feel like maybe I'm supposed to be writing nx there. Alright, well anyway, let me forge ahead here. Then the other term that Nathan threw out is comaximal. Alright. And actually, yeah, I think I should have written there. Curses. Oh, there's something I'm forgetting, Audric, at the moment, but in here, if we took like 3, it would be yeah. It's like 3 plus 3 plus 3. Well, this is by definition nz, such that n is an element of the integers, right? I mean, that's what that is. So it's, I was thinking multiplicatively, but I think I should be thinking additively at the moment at least. Something bothering me, but I can't express it. Anyway, so, fine. So comaximal. What does comaximal mean? So if you have an ideal I and an ideal J, subset of a ring R, then if I plus J, which by the way is x plus y such that x is in I, y is in J, right? It's comaximal if the sum is the whole ring.
I don't like this notation, but it's okay. I really don't. Well, I mean, it doesn't matter, but I feel like it should be sets. But that's just me. Like, it should just be the union instead of the plus, but I might just be annoying.
And this is, now sometimes this is, there's another way to state this. So this is actually, if you look at the Wikipedia article, I was just looking at it, this is not their definition. Their definition is if there exist I and J and J such that I plus J equals to 1, then it's comaximal. It's just I mean, the thing is, if 1 is an element of your ideal, then I is equal to R. Because you have...
Because you can, well, no, never mind, keep going.
Because if you multiply, if 1 is an ideal, and you so let x be an element of the ring, then, 1 times x equals to x is an element of I. So x is an element of I, so the ring elements are the ideal elements, so they're equal. So comaximal means that you can add the two things together and get everything. So,
but how would you get 1?
get 1?
Yeah, like, or the identity element of it.
How can this happen?
Yeah, like.
Oh, okay, so like for 2 and 11 are comaximal. Because there exists 2 times A plus 11 times B, which is equal to 1.
Oh,
what can we choose? I mean, what is it?
33 and 22. B3, A11.
B3, A is
No, minus. One's minus, whichever one. Oh, wait. And 20, 33, 20, and 32, sorry. So A is 16, B is 3. And then one of them is minus. I think the A is minus.
So that gives you 32.
Minus, yeah.
32 minus 32 plus 33 equals to 1, right?
Yeah.
So see then, if you have an integer x, you can rewrite it as minus 16 times 2x plus 11 times 3x, right?
Mm-hmm.
Or should I should really write it this way, excuse me. Minus 16x times 2. Excuse me. I'll get it right eventually. Well, yeah, fine. Minus 16x times 2 plus 11x times 3, which of course is an element of 2 plus 3, right? So but this identity holds for any x, for any integer. So any integer can be written as a linear combination of multiples of 2 and multiples of 3. So for integers, the interface of this stuff with like number theory is that two ideals of the integers are comaximal if the integers which generate them, 2 and 3, are relatively prime. Or to look at it in a different way, you can test for whether or not two integers are relatively prime by checking if the ideals which they generate are comaximal.
What's relatively prime?
Means that
They're added together or multiple?
their greatest common divisor is 1.
Oh.
There are various ways of characterizing it, which will make this conversation more or less circular.
Okay.
But the concept of comaximality. So anyway, the theorem that Nathan uses is just this. So now that we get all this stuff out in front of us, and we at least have a fuzzy notion of what an ideal is. If you have a ring, and you look at the polynomials over the ring, R, right?
Theorem 5.16. Or this is Nathan's paper. Right?
Nathan's paper, I don't remember the number. But a ring, yeah, fair enough, let me tell you.
I have his paper pulled up.
I know, I gotta find it. I don't have it memorized. Here. I got a lot of paper.
Is it 6.6? Page 11?
I can't, I got so many papers open at the moment, it's gonna take me a second.
Yeah,
this
it's
is
page 11, 6.6. That's it.
Which section is it?
Theorem 6.6, section 6. No, that's not right. I don't think that's right.
Which paper is that in?
I'm in his algebra over in algebra. But I'm gonna be wrong when I get this paper. I did not quite finish this paper. I got to almost done. He's talking about zero divisors and this, and then he starts talking about
Armendariz?
Yeah.
I'm probably mispronouncing that too. I was thinking about.
This is the only paper I got to reading, honestly.
Cool. Let's see here, where was I?
And let's see. What are the papers?
Come on.
Okay, there's that paper. And then there's those other two papers. Oh, that's the one. That was the first part.
Theorem 5.5.
On which one?
The doing algebra over an associated algebra. And this is a standard result in ring theory. Now, admittedly, he has the product ideals here. So if you have A1, A2, AN, whatever, then this is isomorphic to R of X, A1. are comaximal, pairwise comaximal. Actually, is that right? What if it's right? So, to give you an example of this theorem at work, if we have like the integer ring z, right, mod 6z. So here, 6 is 2z times 3z, by the way. So when I take the product of ideals is just defined by like multiplication of the things in the ideals. So 6z, of course, you could obtain from 2z times 3z, right? These are equal as sets, and these are comaximal. So this is isomorphic to z cross z, 2z cross z, 3z. So you've seen this in group theory. Z6 is isomorphic to Z2 cross Z3. On the other hand, Z mod 4Z.
Oh, we did. I did this proof with you one of these days.
Right. I mean, I think we ran into this somehow the other day. I forget. I mean, it is true that 2Z times 2Z is 4Z, but it is not the case
They're isomorphic.
that this is that you can, you know, the theorem does not apply, and so the theorem doesn't say this, and nor is it true, you know, because this is the cyclic group of order 4, whereas this is the Klein 4 group, and they're not isomorphic as additive groups. So, like, I think it's really quite beautiful. The way Nathan's corollary 5.7, like the way he works that out, it's really nice. Did I hit record?
Oof. I think you did. But then again, you did your set.
Yeah, got it. So, and his notation is like very compact. I tend to make up different letters and make up isomorphisms and stuff, but he just is like, all right, so what is Hn? Hn, it's really just polynomials in J, quotient by, you know, j to the n minus 1. So with this notation, I mean, okay, so the thing I haven't shown you yet is you can prove that if you have an ideal, all right, a subset of your ring, then if you do like a plus I times b plus I equal to ab plus I, and if you do a plus I, that's plus. That's multiply, circuit scale, sorry, times. And yeah. So I'll just stick with this as the main point, is that this is a well-defined thing. like this, there is a unique thing of the form AB plus I for which it's the product of these two. But that you need that this is an ideal for this to be a well-defined multiplication. If you try to look at the set of cosets, additive cosets, for something that's not an ideal, and you try to use this as a definition for multiplication, then you can get like multiplication which is not single valued. So this is other things here, right? Like for example, 1 plus I times x plus I, by definition, is 1 times x plus I, right? Which, by the way, is x plus I. So 1 plus I serves as identity in what we call R mod I. Now, R mod I is the set of cosets of the ideal. So, anyway, my point here is just that we can look at polynomials and we can divide by the ideal generated by like a polynomial that we want. So when we really work in this space, this gives us a set of things that have real coefficients such that, I mean, essentially this is equal to a0 plus a1j plus a n minus 1 j to the n minus 1 plus the ideal, generated by j to the n minus 1, such that a0, a n minus 1 are real numbers. So what I'm trying to say is that this right here is analogous to like what I'm writing as quote unquote A in this down here, and this is the ideal in question. And you work out this theory carefully in abstract algebra too, right? And you prove things like two cosets are equal, A plus I equal to B plus I, if and only if B minus A is an element of I itself. Alright, but to say that B minus A is an element of I in our context is to say that, B minus A is equal to some multiple of j to the n minus 1. Well, not that necessarily, but a multiple of that. Alright, let me stop blathering. The point is, the thing I'm not clear on at the moment, Audric, is like what kind of multiple I'm talking about. I'm debating in my mind whether I'm not supposed to be talking about an integer multiple, or am I supposed to be talking about a polynomial multiple? Alright, and anyway. So we can construct these spaces this way. Alright. Now, and if they're comaximal, we get this isomorphism, which is kind of cool. And I would point out again that Nathan uses that to very clear isomorphisms there. But actually I don't need this isomorphism stuff for our stupid solution. So here's the thing. So we don't write the plus I, we just write the, we just write the representative, and like we don't write the plus I when we actually work in these spaces. I think I've showed you this before with complex numbers. We looked at polynomial quotients one day,
Yeah.
right? So it's just like that. So if we're, suppose you're looking at a to the n, d to the n, plus an minus 1, d to the n minus 1, a2d squared plus a1d plus a0, all of that acting on eta equal to 0. So, and I'm going to assume that an is a unit, because otherwise I think bad things happen. All right. Now, and this is all for like coefficients in some algebra A. Now, we know we can write down, so basically we're looking for zeros. If we could factor this polynomial in the differentiation operator, great, we could go fall back on section 1, right? If we had an isomorphism to the direct product of algebra, we could fall back on section 2. But what if you don't have either? What if all you have is that you got this polynomial, there's no clear way to factor it, and maybe there isn't a way to factor it either, like d squared plus 1, right? D squared plus 1, we're kind of stuck. D squared plus 1 acting on eta equal to 0, unless you have a number in your algebra such that the square of that number is minus 1, like I, you don't have a way to factor that, right? If that's
Well, we don't have isomorphism.
and there is no element in the hyperbolic numbers, for example, that behaves as I. Like there is no I in R cross R. There's no imaginary unit there.
Yeah. Unless you complexify.
That's right. So what we do is say, okay, well, I take your algebra and I'm going to create a new algebra called do I have a name? I forget if I have a special notation for it or not.
Are you still on Nathan's paper?
Yeah, I'm still on Nathan's paper. I'm page. Let's see here. I call it A prime. All right, so I say A prime. And so I give this whole thing a name, by the way. I call this polynomial, this is the character, I call this P of D, okay? So what I say is, I'm going to go ahead and use Nathan's sleight of hand, okay? So I'm going to say A prime is, what it is it's A of K, so the polynomial is in K, quotient P of K, the ideal generated by P of K. So this will give me an n-dimensional, well, n-dimensional is kind of sneaky, n-dimensional with respect to A space, such that P of K equals to 0. So basically this looks like something of the form, alpha 0 plus alpha 1 K alpha n minus 1 K to the n minus 1, such that alpha 0 through alpha n minus 1 are elements of the algebra, and K to the n, not K to the n, not K to the n generally, but P of K is equal to 0. The thing is, because P of K is equal to 0, I can take the representatives larger than order n and I can collapse them down and just keep the first up through n minus 1 power. And technically speaking, right, like if you want to be picky, this is really like plus I, right? But we don't write that here. This is I. We don't write that because it suffices to write that as my representative, and I can do work on those. But this algebra A prime I call it the characteristic extension algebra. Characteristic extension algebra. And it's something I can construct for any problem or any algebra. So I would get into trouble if I put a zero divisor here. I don't think it's an ideal. Well, there's something bad that happens. Maybe it's not that it's not an ideal, but something bad happens. Maybe it's in the solution set part of this. Let's carry on here. So, okay, so that's an characteristic extension algebra, right? Now, I say, okay, so I can define I said furthermore, this is my definition 5.18. I can define f of, I can let f that goes from A to A prime. All right. Defined by f of zeta equals to exponential of k zeta. I'm not actually defining f at the moment. What I want to define are the component functions of f. So if this is the case, you can write this as f1 plus kf2 plus k to the n minus 1 fn. As I think I call them special functions. F1, F2, Fn special functions. I said that these are the special functions of exponential on E prime. Now, why do I know that there exist? Now, those functions, those functions are a valued. Right? I know I can break exponential k zeta. It is formed from a series over the A prime algebra, and since everything in the A prime algebra can be written as a linear combination over A of powers of k up to kn minus 1, I can just take that formula for exponential and I can split it into like the real part, so to speak, the part that's just an algebra but no k, then the coefficient of k, the coefficient of k squared, and so forth, and then I call those things the special functions of the exponential. But these special functions are actually themselves mappings from A to A. Now, before this point in this section, I had proved a little bit of calculus here, which is that
You were in which paper are we in now?
Nathan's paper, I'm on page 25 of the AOD paper.
Okay. Okay, I'm with you. Oh crap, well, I'll do it 2 fingers right now, I'm not with you. Okay.
So what I have proved is that if you have, let's see here, F composed with G, which is like a mapping from A to A to A prime.
Oh yeah, I remember seeing this.
So the G is like from A to A, and then the F is from A to A prime. I define what I mean. I first of all, in this section, define what I mean by a differentiable. I'm definition 5.15 in this section. I explain what I mean by this right here is definition 5.15. Explains what I mean by a differentiable when we have a function from A to A prime. A prime is the characteristic extension. So it actually just means that the differential is right alinear. Turns out that that still makes sense in this context as a reasonable definition for what I mean by a differentiability there. But notice that is not the same as what we were talking about to start with, because in a differentiable it goes from A to A.
Yeah.
Okay, but anyway, if this is a la definition 5.15, a differentiable, and by the way, 5.15 just says that df d zeta is just e1 df1 d zeta plus e2 df2 d zeta plus en dfn d zeta if, you know, a prime is n, basically isomorphic to e1a, direct sum e2a. And I do think I need also that E1 is the anyway, you should read through that and see if it makes sense to you or not, but without beating a dead horse here. Actually, the horse is not dead. I don't think I've even killed it once yet, but the point is you can make definition for this as it just so happens that this exponential that I've written up here is just such a thing. And all right, so anyway, what I proved then in Theorem 5.16 is simply that if you take the derivative with respect to z of, say, f of g of z, guess what happens? You get f prime of g of z times g prime of z.
Nice little product rule.
Right, but keep in mind that, you know, again, these are functions of, they're not the same, they're not
Wait a
functions.
minute. Doesn't seem right.
Well, notice that f prime here, that f is a function from a to a prime.
I said the product rule. It's the
Oh, chain,
chain.
yeah. Oh, I'm wrong. I'm a dummy.
Oh.
That wasn't it at all.
Oh yeah, it is. You just switched the numbers. You just
Oh
switched
yeah, it's considerably different though.
Huh?
So f was a to a prime, and g was a prime to a prime. So it's supposed to be a prime versus. So I have g from a prime to a prime, f from a to a prime. So this I should do f composed with g, right? So that would go from
No, you did G
no,
composed
G
with
composed,
F.
G composed with F.
I'm gonna write it backwards since I've already written this out.
So G composed with F, and that would be mapping from A to A prime to A prime. Okay, there we go. So now, when I look at GDZ of G composed with F, I get G prime of F of Z times F prime of Z. And that makes sense because this is in A prime and this is also in A prime. So it makes sense. We're taking a product of two things in the extension algebra, which is something you can do. See, because like F prime here, the value of F prime is in A prime. Too many primes. Sorry about that. Anyway, all of this just to say that it makes sense here to say that d zeta of the exponential of k zeta is actually just equal to the exponential of k zeta times dd zeta, ddz of k zeta. So in this problem, the f, so this is f composed with g of z, right? And here the g of z is sorry. Not bad. Should have done this at the start when I was more awake. Alright, well I can't explain anything today, but you sort through the calculus here. It does justify the fact that if you differentiate this function, you really do just get like k times exponential of, you know, k zeta. And I have spent considerable effort to explain this carefully on page 26 here at the top. I really do try to explain how differentiation on the extension algebra relates to the differentiation on the algebra. You know, why we have this chain rule. How it is a generalization of the mixed chain rule that we saw in complex analysis, which is so important to the complex integral. But at the end of it all, we have the derivative with respect to zeta. Ooh, and I actually, I think I'm still specializing it too much, but actually for any, I actually have DD, like if you look at my corollary 5.17, I don't just state it for like k, I state it for an arbitrary alpha in the extension algebra. It's like the derivative with respect to zeta of exponential alpha zeta is alpha exponential alpha zeta. So. Anyway, the point is still true in the extension algebra. So that finally brings me to Theorem 5.19, which I stated for a monic nth order polynomial because I was being lazy, I guess. So Theorem 5.19 simply says that the special functions of the exponential on the characteristic algebra A prime equal to A of k mod P of k are fundamental solutions at for P of D acting on eta equal to 0. And I'm assuming that the polynomial here is monic. So the lion's share of the writing in this section is really just to try to convince the reader that in fact this is not me just making something up. Like this legit goes through with the proper definitions laid down. And then, okay, so fine. You can define these n special functions. So are they solutions to the problem? Well, the special functions are engineered so that P of k is 0. So like when you hit P of D onto the e to the alpha zeta, and instead of saying alpha, let me say k here. So e to the kz, right? Well, because the above is true, this is just going to give you P of k, e to the kz, k zeta. But in the characteristic extension algebra, this is 0 in the characteristic extension algebra. So what this means then...
You got through from the problem without an isomorphism or a...
Right, exactly. It means that e to the k zeta, right, is automatically a solution. It's automatically a solution
to everything in the...
to the a primification of the problem. Like if you look at this is the over a prime
primification
has solution e to the k zeta. Assuming a prime, of course, is built as a of k mod the characteristic polynomial. Because two things, the calculus and the algebra, and that's why this is the stupid solution, because it's like
you're forcing it.
But then, still something to show it's a fundamental solution set. It's not enough, like we need to show that these special functions are necessarily and linearly independent problems, because going back to our existence and uniqueness stuff earlier in the paper, we proved that the solution set to an nth order AODE must include n n linearly independent over A solutions. So how do you prove that the fundamental solutions, the special functions rather, are linearly independent? So that's the next thing I do. Let's see here, so we're at equation 101. So I define the exponential to be h, and I notice that the jth derivative of it is just k to the j times e to the k zeta, right? And also, by the definition of differentiable over a prime, by the definition of derivative of a function from a to a prime, you just differentiate the component functions one at a time. So that means that if I take the jth derivative of this, it's the jth derivative of this, it's the jth derivative of that, it's the jth derivative of that, right? All right. So what do I have here?
What does it mean for the exponential though? That it stay the same?
Ah.
It should stay the same, right? Because you're just taking the
Let's
derivative.
see if I can
Ooh, no.
carve myself out some space here. All right. All right, so I say we have h of z equal to, what was it, f1 plus k f2 k to the n minus 1 fn, and that's e to the kz, right? Oh, da 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 da. I got it. I'm sorry. I've forgotten the argument proof here for a second. No, I got it. Plug in, like, let's just look at this one, right? Plug in 0.
You get 0, or you get 1.
So we get f1 of 0 plus k f2 of 0 plus k n minus 1 fn of 0 equals to 1. Now, remember, it all goes back to this. When you work out the ring theory carefully, you can prove that 1, k squared, k to the power n minus 1, this is linearly independent. So,
Gotcha.
that forces f1 to be equal to 0, excuse me, 1, and f2 of 0 all the way up to fn of 0 to be 0. All right. Now you take this and differentiate once. All right, differentiate this once. That gives us that f1 prime of 0 plus k times f2 prime of 0 plus k to the n minus 1 times fn prime of 0 is equal to, what happens when we differentiate this? Well, we get k e to the kz, right?
Yeah.
Evaluate that, it's equal to 0, you get,
0.
not 0, but k. We're
Oh,
putting
yeah,
z,
that's right.
z equal to 0. Now, we get to equate coefficients using linear independence of the 1 through k to the n minus 1 basis. See? This equal to that. And this time, the story is a little bit different. This time, f1 prime of 0 is 0, and f2 prime of 0 is 1. Right? And the rest of them, are 0, right? And then you differentiate again. And that gets you the k squared. It gets you a k squared on the right hand side.
Yeah.
And so,
That means that F3, and so on and so forth for every.
right, so I write this compactly, this pattern compactly, as saying, oh, so if we take the ith component function and we differentiate it j times, and we evaluate it at 0. Chronometer delta. The end of the world. It's not the price you wanted.
Studies cancelled tonight. Church is all out.
Oh. I'm sorry. Well, we can work longer if you want. So,
Yeah,
this
let's finish the paper for sure.
this is the pattern.
Mm-hmm.
All right. So, you with me? So what's the Wronskian of F1, F2, Fn
Do you get one of these?
at 0?
You want one of those?
The Wronskian is something legitimate to look at here.
Well, it's not
Is that
zero.
okay?
It's legitimate to look at here because these are solutions.
Mm-hmm.
So prove they're solutions. There's n of them. So this is either identically 0 or it's identically a 0 divisor or it's identically a unit. And if it's identically a unit, they're linearly independent.
Yeah.
But if you look at this is the determinant of what goes in the top row. It goes
You opened it.
F1 of 0. I opened this. I opened this. I will open this, you bet you. Because I'm hungry, and I really could use some gummy candy. So I appreciate you bringing me this gummy candy for my evening.
No, it's mine.
Oh, it's yours? Are you sure?
Yes.
But I was hungry for gummy candy.
But I'm
And I'm sure that Audrey's coaches tell him you gotta eat a lot of gummy candy. That's where
Yeah.
the speed comes from.
Yeah.
that is what?
This is all for us,
It's
Benjamin.
made out of food. It's made out of food.
Well, I appreciate you bringing it to us, Benjamin.
Hey, it's mine.
About to fall on the floor. If those fall on the floor, I'd be in big trouble. So the top, the top row here, F1 of 0, F2 of 0, right?
Mm-hmm.
Fn is 0. And then the next one is like F1 prime of 0.
Oh, so you just get diagonal, yeah.
Uh-huh.
Mm-hmm. So that means the determinant's not 0.
Right, so this is, subject to the calculations above, it's just 1's down the diagonal, which is equal to 1, linear independence.
Yeah.
And, so
You
like,
don't run into the
I was happy at one point with Nathan, like he come up with, because Nathan's, a lot of this, most of this, like is the thinking of doing it this way was very much Nathan's idea. And then I'm like, oh, but now we gotta prove they're linearly independent, and I'm like, because the calculus fell through, and I was like, okay, good, and then I was like, oh, well, we still need to prove they're linearly independent, and then I was like, how do I take that? Oh. And then this happened. I was just like, it's not bad. And that's why this is the stupid solution, because not only is that a solution, it is a solution that contains in its component functions the general solution to the problem.